Hello, everyone. Nice to meet again. My name is Joshua, and it's my pleasure to welcome every one of us to this short video on how to estimate traditional TFP and green TFP using stochastic frontier approach. Let's set our working directory straight away. Go to session, set a working directory, choose directory. I'm using this basic R folder. It's on my desktop. That is my directory. So let me open it. All right. So then let's load the necessary packages. We need the frontier package for the stochastic frontier analysis. We need the tidyverse for data manipulation. We need the forecast package to auto plot the graphs. Summary tools for descriptive statistics. Then, in case we want to produce the graphs in a table, then we need gridExtra. In case we want to look at the determinants of the TFP using autoregressive distributed lag model, then we will need the ARDL package. So these are just the packages. So let's load them. In case you don't have the packages, or maybe you have part of it, whatever you do not have, just click on choose here, then install packages. Then type the package that you don't have here, then install. I have all of them, so I don't have to worry myself about the installation. But don't forget, in case you want to install, be sure that you are connected to an internet. Now let's get the data sets. I named the data green data. Sorry, click on file here so that I can have all the data sets in the folder. Okay, this is green data, so click on it. So import. So import the data set. So here we have the data set. Let's return to our script file. Now you may want to make some corrections on the data set if you so wish, or maybe you just want to look at the spreadsheet to look at the data itself. You use this function fix. So let's run this. So here we have the spreadsheets. So you can change anything here. You can change anything. So, but I'm not interested in changing anything. So let me just let me close it. All right. Yeah, we need to remind ourselves the column names, that is the names of the variables, so that we are not making spelling mistakes. So we have 25 different variables. We have the year, the value of agricultural output, that is VAO, crop outputs, animal output, labor, pastoral, and so on and so forth. So let's fix idea. Let's say our first objective is to conduct a descriptive statistics of the time series data. In that wise, we will need the summary statistics as well as the trend. So for the summary statistics, that is why we load the summary tools package. So this is our object, that is the data set. The function to produce the summary statistics is DESCR. It's going to automatically extract all the quantitative variables. I put stars equals to common here, that is produce common statistics. If you don't put it there, it's going to give you so many statistics, kurtosis, skewness, mean absolute deviation, so many. But with common, it's going to limit us to common ones. Then transpose. Transpose means I want the statistics to be the column, while the list of the variables will form the rows. So let's run it. Fine. So to produce the statistics in Microsoft Word, so you say we use view. So this is the stats tool that we have generated. File equals to, let's change this to 3, because since I've generated it before, it's going to maybe deny us from getting the results if you still maintain that too. So you can call it any name of your choice. So I call it stat3. .doc means I want it in Microsoft Word format. That's Word documents. So run. Beautiful. You can see that output file written this where is saying that this file is now written in your directory. So let me update this my directory here. Then I will look for stat3. Stat3. So this is it here, stat3. So let's open it. Beautiful. So here we are. This is the descriptive statistics. So the common statistics produced are mean, standard deviation, minimum, median, and maximum, as well as the number of observations. So this is super clear. So let's close this and let's return to our. So the next thing, we want to transform the variables to log form because we want to estimate the frontier production function using a Cobb-Douglas production model. So this is, we transform the log of the dependent variable to Ly, labor to LB, land to LH, capital, and so on and so forth. So let's. So, and please take notes, I generate the trend. I say trend is equal to year minus 1990. Our data start from 1990. So for the trend, it's going to be 0, 1, 2, 3 up to the last year. The difference between the last year and the 1990. The essence of the trend is for us to be able to estimate the technological change component of the TFP. So let's run it. Fine. So let's plot the time series. Now for the output, what we are trying to do here is to make sure that we transform the log variables into time series using the TS function. So I call it L1_TS. So we have TS. This is our green data dollar. This our output. The starting year is 1990 and the frequency is 1. So let's run this and auto plot. I call it the first plot, which is P1. This is the label. X is year. Y is the log of output. Then this is just changing the theme for the graph. So let's run this to generating the P1. So this is the plot. Yeah, so where we have the plot, so I think it's clear. So this is exactly what we need to generate. It's just a matter of copying this and replacing it with the other variables. For instance, now we translate the large to time series and we plot and we call it P2, and we do the same for all the other variables until we reach P6. So in essence, let me run it from P1 to P6 straight away. All right, so run. Good. So the next thing we want to do is to ensure that all the 6 graphs are presented in just a table. That is why we want to use the gridExtra package. So using the grid.arrange function. So I say, okay, arrange it in 2 columns. So run. So here we are, so 2 columns. So we have all the variables here. So those are the graphs, and in case you want to take it to Microsoft Word, just click on Export, copy to clipboard, and then copy plot. Then you paste in Microsoft Word and make necessary adjustment that you want to make and label. Yeah, so now let's say the second objective is to estimate the traditional TFP, and lest I forget, the data we are using is for Nigerian agricultural sector. While is the value of the agricultural output, the data are well obtained from FAUSTAT. So we have the stochastic frontier. This SFA is the function needed to estimate it. I've included the trend to be able to estimate the technological change. You know, the TFP has 2 components. We have the efficiency change and the technological change. So let's run this and get a summary. Let's move this so that we can see the result clearly. Okay, enough. So run. All right, so here we are. So we look at the results, and we can see that the results are statistically significant apart from trend. And don't forget, since the variables are included in log form, we interpret the coefficient in terms of percentage change. So a 1% change in labor, for instance, will lead to 1.008% change in the value of agricultural output for Nigeria, and so on and so forth. That is just the way to interpret that. And if you look at sigma square and gamma, is actually showing that inefficiency is important to the model. So, and if you look at the mean efficiency is 0.94, which is actually showing us that the agricultural sector in the economy, in terms of the efficiency, can still be improved by about 6% using the currently available resources. So let's move forward. Now we want to extract the TFP, where we need to extract the TFP from the stochastic frontier function that we have estimated. To do that, we extract the efficiency scores. That's what I call EFF1. The function is efficiencies. We obtain the efficiency change But don't forget, since our function is in log form, so we first obtain the log of the efficiency change. So, and it's the first difference of the efficiency scores. And don't forget the first, since it's first difference, the first observation actually will be missing. So that is why we include NA here. The technological change is the coefficient of the trend, as I told you that earlier. So this is how to extract it, this coefficient of the model we have estimated for trend. The moment we have done that, it's just a matter of converting the log efficiency change and log of technological change to efficiency change and technological change by taking the exponent. So that's why we have exp here. So the moment you have done that, we all know that our TFP is the product of the efficiency change and technological change. So that is just the procedure. So let's run it. So and let's produce the first 6 observations. Good. So here we have the first 6 observations. That's all right. So that is, we have obtained the traditional TFP, that is the traditional TFP. To estimate the green TFP, the basic difference is that in the modeling, we now include carbon dioxide emission. So this is just the difference. Every other thing is the same. But I call it SFA_EMV, excuse me, to indicate that we are now considering the environmental factor. So let's run it and obtain the results. So good, you can see that there is a slight increase in the mean efficiency when we included the carbon dioxide emission. Yeah, peradventure, maybe the nation is actually doing a lot to ensure that the carbon dioxide emission from agriculture is mitigated against. Yeah, so let's move forward. And just like what we did the other time, we extract the TFP green now, just following the same procedure. We have the efficiency scores, just like before. Then we have the efficiency change, just like what we did the other time, actually. So we follow the same procedure then until we obtain the green TFP as the product of the efficiency change, the technical change. So and let's get the forces observations, just like before. So here we are, so you can see the difference. And if you look at the estimate, you can see that for various years, the estimate of the green TFP is slightly higher than that of the traditional TFP. Let's run the forces observation for the two to make it easy for us to compare. One thing you will notice is that the first observation is NA, because they are actually the first difference. But it's supposed to be 1, because by means of interpretation, we just need to subtract 1 from this figure in order to interpret. For instance, now for this year, 1991, for instance, the TFP is increasing at the rate of 9.67%, whereas the green TFP is increasing at the rate of 9.72%, and so on and so forth. So for ease of interpretation, this is supposed to be 1.00. This is what we are trying to do here. So we say green underscore data dollar this is.na, the same as we have here, is equal to 1. That is, change this NA to 1. Then we repeat that also for the TFP, and we obtain the forces observations. So let's try to do that now. You see that you can see that it has changed to 1 instead of NA. So having done that, then you just need to plot. So just like what we have before, in this case now we try as much as possible to transform the TFP and the green TFP to time series. So that's why TFP is equal to TS as the function. We have our TFP, the starting year is 1990. The same applies to the green TFP. Then we combine TFP, green TFP. Then we auto plot and label just like what we did before. So if we have done that correctly, so let me move this so that we can see the graph clearly. Good. All right, so you can see the graph now. This is for the TFP and the green TFP. So that is showing the graph. So another thing that we can do, we may want to look at what actually determines the green TFP or TFP, depends on the interest. So if you are looking for the determinants, then the starting point is to now take the unit roots. No, don't forget we are dealing with time series, so that we will not be running kind of spurious regression. So we are using URCA package as unit root co-integration analysis package. So run. Let's remind ourselves of the names of our various columns. So to perform the unit roots, UR summary. This is for ADF, auto Decomposition. So we are trying to do that for TFP green. If you look at the graph, maybe it's showing some kind of trend. So let's start by maybe considering the trend. So we run it. So if you look at it, this is minus 4.3217, and it's higher than, in absolute terms, it's higher than this minus 4.15. So which means it's stationary at level. So if you want to consider the constant alone without taking into consideration the trend, that is why we have the drift here. So again, just a summary. Just change the, so and this minus 3.58 here. So look at the value. So the value also is minus 4.5, minus 4.38, which is higher than minus 3.58 in absolute terms. So confirming the fact that the green TFP is stationary at level. So now for inflation, we repeat the same. So let's look at inflation. So for inflation, for instance, Yeah, you can see this minus 3.601. In absolute terms, is less than this 4.15, which means it's not stationary at levels. So we try to take the first difference. To take the first difference is DIFF. So let's try to do that. We can do that for trends and for drifts. So run. So nice. So we can now see that it's stationary after the first difference. So in essence, the TFP green is I0 integrated of order 0, while inflation is integrated of order 1, I1. So with the presence of this mixed order, for instance, it suggests the use of autoregressive distributed lag. So we need ARDL and DLAGM packages. So let's run. So we need to determine the lag order we want to use for both the dependent variable, in this case, our green TFP, as well as inflation. That is why we have this auto underscore ARDL. So we start with the maximum order of 3. So let's run it. So then we can obtain this lag D dollar top orders to look at different orders. So the base order is actually 1, 0, followed by 1, 1. So I've chosen 1, 1 for my autoregressive distributed lag model. So lag my TFP, green TFP by 1 year, and sorry, this will be inflation, INFL by 1 year. So let's run this and get the summary. All right, so we can see that from this graph, for instance, now, 1 year lag of the TFP strongly determines what happened to the green TFP actually. We may want to conduct the F test for co-integration. So that's the band F. So let's run it. Now, if you look at the F statistics, is 44.75, which is greater than the lower band and the upper band. If you look at the p-value, 0.000 something. So which means that there is long run relationship between inflation and green TFP. So, and since we have established that, then we need to extract the long run relationship as well as the short run. So for the long run, just multipliers, run. So this is the estimated long run, which is, if you look at the t-value is 0.34 in terms of the p-value, it's actually showing that it's insignificant. So that is in the long run. But let's look at the short run. That's the restricted ECM. So they got the summary. So run. So in fact, the adjusted R squared is 9, so you can now see clearly. So all the same is insignificant. So in essence, both in the long run or short run, inflation does not really affect green total factor productivity. Yeah, we may want to include other variables or test other variables and so on, but this is just showing the procedure to carry it out. So in terms of various diagnostic tests, so we use this ARDL band. Yeah, sorry, I'm using INFL. So that's, yeah. So let's run this. So you can see various statistics. We have the normality test, Shapiro. We have the uh, autocorrelation of the residual test using Box-Legion tests, and so on. So you can actually extract some of those tests. Yeah. So in essence, this is just the procedure. If you are interested in estimating the determinants of the TFPs, you can include as many variables as possible if that is what you want to do. But don't forget, the moment you include more variables, then you have to go back to where you determine the maximum black order to use and all sorts of things. So thank you very much. I hope we have learned one or two things. So thank you. Till we meet again. I'm yours, Joshua.